Welcome to our Quantum Deep Dive. Today we're plunging into a topic that honestly sounds like it's straight out of science fiction.
It really does.
But it's very much rooted in some pretty cutting-edge research.
Yeah.
We're talking about quantum semantic similarity
Mm-hmm.
and, what it could mean for the next generation of natural language processing, or NLP.
Yeah, it's fascinating stuff.
Our deep dive today is inspired by this really interesting essay. It's called Quantensemantische Ähnlichkeit, NLP der nächsten Generation. It's by Jürgen Schneeppert.
Right.
And it asks this, pretty profound question. Can the really bizarre, sort of counterintuitive rules of quantum mechanics actually help computers genuinely understand human language? Like, really understand it?
Indeed. And that's sort of our mission today, isn't it? To unpack why even our best traditional language models, they still grapple with the subtleties, the nuances of how we communicate.
Yeah, they're amazing, but they still trip up sometimes.
They do. So we'll explore how these quantum principles might offer maybe a revolutionary new framework to get past those hurdles.
Okay.
What's really fascinating here, I think, is how concepts from the subatomic world might unlock a deeper, more fluid understanding of meaning itself, something closer to how we humans actually perceive it.
Okay, so let's unpack that. Before we jump into the quantum weirdness, maybe we should talk about why current AI struggles.
Good idea.
Even with all its brilliance, why does it stumble on something that seems fundamental? Like truly understanding meaning. You've probably seen examples, right? Chatbots getting context totally wrong.
Yeah.
Or search results just missing the point of your query.
Absolutely. It happens all the time.
That's where semantic similarity comes in. So what exactly is semantic similarity, and why is it such a persistent challenge for computers?
Well, semantic similarity, it's basically how words or sentences or even whole documents relate to each other based on their meaning.
Okay, meaning not just the letters on the page.
Exactly. Not just their literal form. So, for instance, car and vehicle, different words, but semantically they're very close.
Obvious to us.
But for computers, there are some core challenges. I'd say the biggest one is context dependence.
Right.
A word's meaning isn't fixed. It shifts, sometimes dramatically, depending on how it's used. Think of the word bank.
Okay.
If I say, I sat on the riverbank, you immediately know I mean the side of a river.
Yep.
But if I say, I deposited money at the bank, your brain instantly switches to the financial institution.
Automatically.
Right. Traditional models often, they miss this fluidity. They might treat bank as just one single thing.
So it's not just about knowing the different dictionary definitions. It's about instantly getting which one fits based on the other words around it.
Precisely. And that naturally leads to the next problem. Ambiguity, or what linguists call polysemy.
Polysemy, right. Multiple meanings.
Yes, many words, especially in languages like German that the essay uses as examples, have multiple, very distinct meanings. Take Schloss. It can mean a grand castle or just a simple lock for a door.
Big difference.
Huge difference. And classical models, they typically assign a single static mathematical representation, usually a vector, to each word.
A point in space, sort of.
Kind of, yeah. And this fixed representation, it really struggles when a word has these multiple, often totally unrelated meanings.
It's almost like, traditional NLP is perpetually stuck asking, are you a castle or a lock? When a human just knows from the context.
Exactly. It highlights just how intuitive language is for us and how frustratingly complex it can be for machines.
Yeah.
And there's one more thing. Uncertainty. Or vagueness.
Oh, okay.
Human language isn't always precise, is it? We communicate in shades of gray with implicit meanings, probabilities.
Sure, hints and suggestions.
Right, our interpretation allows for that ambiguity, that fuzziness. But classical models, they're usually built on very precise deterministic logic. They can't really explicitly capture that uncertainty. They try to force a definite answer, even when maybe there isn't one.
Okay, so given those challenges, context, ambiguity, uncertainty, what tools have we actually been using to try and tackle this? Because we have made incredible progress.
Oh, absolutely. We've come a long way.
We started with things like vector space models.
Yeah.
Right, where words are points in some high-dimensional space, and similarity is like how close they are.
Yeah, or the angle between their vectors, cosine similarity, and things like that.
Then there was latent semantic analysis, LSA. That used some pretty complex math, I remember. Singular value decomposition.
Right, SVD. To find these hidden semantic structures by looking at how words appear together across huge amounts of text, basically trying to distill meaning from co-occurrence patterns.
And then more recently, things like word embeddings, word2vec, glove, fast text. They really changed the game.
They absolutely did.
These models learn these dense vector representations that capture really cool semantic relationships. The famous example is king minus man plus woman equals queen mathematically.
That was mind-blowing when it first came out, and these embeddings revolutionized so many NLP tasks.
But. There's always a but.
There's always a but. Despite their successes, these methods, fundamentally, they assign a single static vector to a word.
Regardless of context.
Regardless of the specific context it appears in. And that's the core limitation we keep coming back to.
Okay.
This fixed representation means they inherently struggle with those polysemous words, the multiple meanings, and they can't explicitly model the sort of inherent uncertainty and the dynamic nature of human language.
Right.
So it raises this important question. If meaning itself is so fluid, so context dependent, how can a fixed static representation ever truly grasp it?
It's like trying to capture a flowing river with a single photograph.
That's a great analogy, yeah.
Okay, so this is where it gets really interesting. Potentially revolutionary.
Mm-hmm.
What if the very principles governing the subatomic world, quantum mechanics, with all its probabilities, superpositions, weirdness, could offer a completely new way to think about the meaning of words?
That's the core idea.
Yeah, that's the heart of quantum semantic similarity. The essay proposes that quantum mechanics offers a truly alternative mathematical foundation, one that's naturally suited for dealing with the uncertainty, the context, the probability inherent in language.
Exactly. It mirrors the messy, intuitive, probabilistic way that we understand language.
Okay, so how does that work? Can we connect some quantum concepts to language?
Let's try. So take superposition. In quantum mechanics, a system can be in multiple states at the same time, right? Until you measure it.
The famous Schrodinger's cat idea, kind of, both alive and dead.
Sort of like that, yeah. The analogy here is that a word can hold multiple potential meanings simultaneously. Like our bank example, it could exist in a state of superposition, embodying both the riverbank and the financial institution at the same time.
Whoa. Okay, so a single word isn't just assigned one fixed meaning in the system's memory. It's held in this state of potential, containing all its possible meanings.
Until the context tells it which one to be.
That's a really profound shift in how you'd even think about what a word is in a computational model.
It absolutely is, and that leads directly to the next concept, the measurement process.
Okay.
In quantum physics, making a measurement forces the system into one definite state. It collapses the superposition.
Right. The cat becomes either alive or dead when you look.
Exactly. In language, the context, the surrounding words in the sentence acts like that measurement. It collapses the word's superposition of meanings into one specific interpretation.
I see. The sentence itself performs the measurement.
Precisely. We also talk about Hilbert spaces. These are the high-dimensional mathematical spaces where quantum states live.
Okay, so like vector spaces, but more complex.
Much more complex and more powerful. Think of them as these incredibly vast, flexible arenas where meanings, represented as quantum states, can interact and shift in ways classical vector spaces just can't accommodate. They offer much greater expressive power for nuance.
So it's not just a bigger space, it's a space where meanings can actually sort of blend and interfere with each other in more complex ways.
Right.
Like waves.
That's a good way to think about it, yeah. Quantum states have wave-like properties. And finally, there's the concept of non-classical probabilities.
Okay, how are they different?
Well, unlike traditional probability where things are just A or B with certain chances, quantum mechanics allows for probabilities that are interconnected, that can interfere with each other. This is crucial for language, which is often vague and ambiguous.
Where meanings aren't just either, but might be subtly linked.
Exactly. Classical models often struggle to assign precise probabilities when meaning is inherently fuzzy. But quantum probabilities are kind of designed for that inherent uncertainty and interference between possibilities.
So, putting it all together, what this means for language is a complete rethink of how we model meaning itself.
Right.
Instead of trying to force a word's meaning into a fixed box, you let it exist as this probability cloud, this superposition, fluid, adaptable. And it only settles into a specific form when the context, the sentence, effectively measures it. This feels like it's not just a small tweak, it's a fundamentally different approach.
It is. It aims to mirror how humans handle ambiguity much more closely.
Can we dive a bit deeper into the modeling? How does that actually look conceptually?
Sure. So in these quantum semantic models, a word isn't just that fixed point, that vector. It's treated as a quantum state mathematically. It's a vector, but in a Hilbert space.
Okay.
And this structure allows a word to inherently represent multiple potential meanings at the same time, each with a different probability or amplitude. They exist in this dynamic blend.
Can you give us that bank example again, but maybe with the quantum notation? How would that superposition look?
Okay, conceptually, you might represent the state of bank. We use this bank notation called a ket as a superposition. Something like bank, Alpha Sitzgelegenheit plus Beta Finanzinstitut.
Where alpha and beta represent the probabilities, sort of?
Roughly, yes. The squares of these amplitudes relate to the probabilities, so it holds both possibilities. Sitzgelegenheit, seat, and financial institution simultaneously.
Right, until
the sentence appears. Say, I walked along the bank of the river. That context acts like a quantum measurement. It effectively projects the state onto the relevant meaning.
it causes the superposition to collapse.
Exactly. It collapses into the specific meaning riverbank. The model isn't guessing. It's dynamically resolving the ambiguity based on the contextual measurement.
That is incredibly powerful. And you mentioned density operators before. They handle the fuzziness, you said.
Yes, exactly. Density operators are a really important tool from quantum mechanics. They're perfect for describing systems where you don't have complete information or where the system is in a mixed state, a probabilistic mixture of different quantum states.
Okay, so not just a pure superposition, but maybe a mix of possibilities.
Right. In quantum semantics, this is incredibly useful. Instead of just a single state vector, a density operator can represent a whole probability distribution over different meanings. It explicitly models that fuzziness, the uncertainty.
So it captures the shades of gray.
Precisely. It allows the model to represent vagueness, nuances, the probabilistic nature of meaning in a way classical models really struggle with. It's not just one definition, but a whole spectrum of possibilities, weighted by likelihood.
Wow. Okay, so summing that up. Instead of teaching a computer separate rigid meanings for bank and just hoping it picks the right one based on statistics, a quantum-inspired system could naturally hold all the possibilities in this probabilistic superpositional state.
Yes.
And then the context dynamically resolves it. That dynamic flexibility seems like a massive leap. For better word meanings, context processing, handling uncertainty.
It really targets those core weaknesses of classical models. It's about embodying the potential of meaning, not just a fixed outcome.
All right, now that we understand the how, the quantum concepts and modeling, let's talk about the what for. Where could this quantum semantic similarity make a real difference? What applications could it revolutionize?
Well, the potential impact is pretty significant across many areas of NLP. Take information retrieval, so search engines.
Okay.
Imagine a search query where the system inherently understands that your keywords might have multiple interpretations.
Right.
It could use superposition to efficiently represent these ambiguities, and then use something like quantum measurement, guided by the full context of your query, maybe your search history, to retrieve the most relevant documents.
So it's moving beyond just matching keywords to actually matching the intent behind the search.
Exactly. If you search for Apple, a quantum-powered system might be much better equipped to figure out if you mean the fruit or the tech company based on subtle clues.
Okay, that makes sense. What else?
How about automatic text classification? Classifying news articles, emails, things like that? A document could, conceptually, exist in a superposition of multiple categories. So a complex news article might simultaneously be, say, 70% tech news, 40% business news, and maybe 15% social impact.
So not forced into just one box.
Exactly. It allows for much more nuanced, context-dependent classification, a richer representation than just assigning it to a single rigid class.
That sounds much more realistic for complex documents. And what about sentiment analysis? That always feels a bit crude sometimes, just positive, negative, neutral.
It often is crude with classical methods, but think about a review like, the design is great, but the battery life is truly awful.
Yeah, mixed feelings.
Very mixed. A classical model might struggle, maybe average it out to neutral, which isn't right. A quantum model, though, could potentially represent this as a superposition. Sentence is gamma 1 positive plus gamma 2 negative.
Capturing both layers at once.
Potentially, yes. Capturing that complex, mixed human feedback more accurately. And practically, these ideas would likely leverage concepts from quantum machine learning. We might see quantum neural networks, or perhaps more realistically in the near term, hybrid approaches.
Hybrid, meaning?
Combining classical AI strength with quantum principles for specific tasks. And people are working on this. You see groups like IBM, Quantum NLP, Cambridge Quantum Computing, Google Quantum AI. They're all exploring these ideas. Experimental implementations are happening.
Okay, so it's not just theory. People are actually trying to build this stuff.
They are. It's early days, but the research is active.
Now, this all sounds incredibly promising. Almost too good to be true, maybe. I assume there are some major hurdles.
Oh, absolutely. Huge hurdles.
What are the main challenges stopping quantum semantics from, taking over NLP today?
Well, first and foremost, computational complexity. These quantum calculations, they're just vastly more intricate and demanding than classical NLP algorithms.
So they need serious computing power.
Immense power. Which brings us straight to hardware limitations.
The quantum computers themselves.
Exactly. Current quantum computers are still very much experimental. They're in an early phase. They have a limited number of qubits. The basic unit of quantum information, maybe only hundreds.
Which isn't enough for massive language data.
Not even close for the scale we need in NLP. And crucially, they're very error-prone. They suffer badly from something called decoherence.
Decoherence. What exactly is that again?
It's essentially the loss of those special quantum properties like superposition and entanglement when the quantum system interacts with its environment noise, temperature fluctuations, anything.
So the delicate quantum state just falls apart.
Pretty much. It collapses too quickly before the computation is finished, leading to errors. So current quantum hardware isn't stable enough or scalable enough for the massive data sets and complex computations we need for real-world NLP. They're amazing for certain very specific scientific problems, but not yet ready for prime time in language processing.
Okay, massive computation needs, fragile hardware.
Well, there's interoperability. How do you actually integrate this fundamentally different quantum logic with all the existing classical AI systems we rely on?
Right, they don't just plug and play.
Not at all. It's a huge technical challenge, rethinking the whole architecture. And finally, there's a significant interdisciplinary gap.
Meaning?
This field demands deep expertise across quantum mechanics, computer science, and linguistics. People who understand all three are rare. Building teams with that combined knowledge is a real bottleneck.
Okay, so those are some pretty formidable challenges. Computational cost, hardware limits, integration issues, and finding the right expertise.
They are significant, yes.
So what does this all mean for the future then? Is it just a cool theoretical idea, or is there real hope?
Despite the challenges, the outlook is actually incredibly promising, I think. The key is that quantum computing itself is advancing incredibly fast.
We keep hearing about breakthroughs.
Exactly. There are constant improvements in qubit stability, error correction, scalability. It's a rapidly evolving field, and this progress could eventually lead to what people call quantum advantage for NLP.
Quantum advantage. The point where quantum computers actually do outperform classical ones for specific tasks.
Yes, for certain complex language tasks where classical methods hit a wall, maybe understanding deep ambiguity or complex reasoning based on context.
So not necessarily replacing everything, but tackling the really hard parts.
That seems the most likely path, especially in the medium term. The essay suggests, and I think it's realistic, a future dominated by hybrid models.
Ah, back to the hybrid idea.
Yeah, we probably won't throw out brilliant models like GPT or BERT. Instead, quantum principles run on specialized quantum hardware or simulators could augment these large language models.
Like a quantum coprocessor for meaning.
Kind of. Handling those specific tricky aspects of meaning, ambiguity, context, and probability that classical architectures struggle with. The ultimate goal here, the long-term vision, is for machines to understand meaning on a deeper, truly probabilistic level.
Moving beyond just recognizing statistical patterns in text.
Towards genuine context comprehension. Understanding the why behind the words, not just predicting the next word. And that could fundamentally change how machines interact with us, with human language, taking them a step closer to something resembling human-like intuition.
And that brings us to the end of our quantum deep dive. Wow. We've journeyed from the limitations of today's language processing all the way to the mind-bending potential of using quantum mechanics to understand meaning.
It's quite a trip.
It really is. It's a field, as you said, still in its early stages, definitely facing huge technological hurdles, but it's one that genuinely promises maybe a revolutionary shift in how machines engage with our incredibly complex human language.
The potential is certainly there.
So here's a final thought to leave you with. Will quantum semantics ultimately lead to AI that truly understands what we say in the way humans understand, or will it just make them exponentially better at predicting words and sounding human-like?
That's the big question, isn't it?
It really is. And it's one that invites you to keep exploring, because the answer, whatever it turns out to be, might just reshape our entire digital world. Our deep dive today was based on that insightful essay, Quantensemantische Endlichkeit NLP der nächsten Generation by Jörg Schneepath.
A fascinating read.
Absolutely. If you're as intrigued by this topic as we are, you can find more of Jörg Schneep's work and delve deeper into these concepts over at his website, schneepat.de. That's SCHNEPPAT.de.
Well worth checking out.
Definitely. Thank you so much for joining us on the deep dive. Until next time.